the good old days of using a whiteboard or chalkboard and stuff like that, because it is kind of cool that a professor can prepare the material instead of having to write everything on the board. The downside was, as soon as the professor is done talking about whatever is on the transparent sheet, the professor can now take that sheet away and then slap another one on top. Okay? So from your perspective, it totally sucks, because if your math professor today, okay, is using like all three of these whiteboards, well, the professor can only write so fast on a whiteboard, right? And you can usually keep up, at least, to a reasonable, rate, okay? But when the professor has everything pre-printed on a sheet of paper and it's all filled up using like 10-point, font, then there's no way you can actually capture all that text, fast enough before the professor takes that away and then slap the next one on. But this is also, now I can try to do that with the projector, but you got two things going on your side. One, you got your cell phone, okay? And the cell phone these days, this is bright enough for most cell phones to capture an image, okay? One. Two, there's enough resolution. Okay, most of your cell phones are at least 1080p, in terms of resolution, if not a lot better than that. Okay, so you take a picture, and now you have everything, and you can either write the notes later, or you can just print it out or whatever, right? Well, back in those days, we did not have cell phones. And the second thing that's going for you guys is I'm using OBS, and we are streaming right now. Okay, so unless I forget to turn it on or there's some technical difficulty that I cannot record it, you got everything on YouTube, okay? Except for the things where I just kind of point out in class using my finger, okay? But other than that, you got everything. Well, back in those days, there's no YouTube. YouTube did not exist. Okay? Yeah. So on top of all of that, okay, this particular professor has the most monotonic voice ever. And he doesn't move, he doesn't walk around, he would just sit next to his computer or projector, and he would start kind of mumbling about things. Now here's the killer part, okay? As if all of those things added up is not enough. This is the killer part. The killer part is when he's thinking, when he's going like that, he would use his pencil or pen or whatever to draw circles on the projector device. Now, it would be somewhat equivalent to what you're seeing here, okay? Except you're not looking at a small pointer going around. You're seeing a gigantic shadow of a pencil going around and round and round. So we had a class of 60, okay? So in the University of Hong Kong, we go by cohorts, okay? So the entire group of 60 people move from one year to another year. So we had a cohort of 60 people. 30 would usually show up in class. Of the 30, about 10 would stay awake the entire time. So, no. I would show up, I would be on the front row and be the first one to fall asleep. So I totally understand if someone is falling asleep in my class, and it does not offend me a bit. Fun stuff, fun stuff. Okay, so getting back to assembly language programming, that's good. So we are now getting back, and let me see, I'm just going to find to class. And we talked about RAM and ROM last time with this class, so the order of topic is a little bit different for this class compared to my Monday, Wednesday class. So what we'll do today is to continue to talk about multiplexers and demultiplexers. I think we talked about those too, didn't we? Okay, so we are actually ready to talk about the processor. And that's why we got a new lab. So the lab that you're going to do today, which you have a whole week to work on, is this one. It's the familiarization with the TTP toolchain. TTP, by the way, stands for Tax Toy Processor. Okay, I think we might have talked about that term a little bit already. Okay, so this is nothing more than just having you guys to follow a few steps and to try to figure out things along the way. Okay, and it's also designed to be to have certain holes in the descriptions so that you have to kind of think about things a little bit to try to figure out the answer. Okay, but in the lab, if you kind of don't want to spend too much time, you can raise your hand and I can come help you, try to figure out some of those things. All right, so that's the tool chain. So what we'll do today in class is, first of all, I'm going to take row, okay? And this is the row sheet that I collected last time. So I'll use the same thing. You just have to initial next to your name already, okay? If you were missing last time, then you want to add your name to the second sheet of paper, okay? There we go. All right. Cool. All right, so what we want to do is to focus on the process now, okay? Which we have already started to do last time. And so the way I explain things in class and the way things are presented is now taking an interesting turn, okay? Because before I have those modules, right? I wrote a lot of modules to explain what is the double representation, okay? What is signed versus unsigned representation, how to add and how to subtract in binary, blah, 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 okay? But from here on, I don't have a whole lot of writing, okay? Then you go like, why? Well, because this is a much better tool to explain everything than I can do with writing, okay? So I will tell you guys how to study, for this class, from this point on. But basically, the processor is its own documentation. Once we understand how each individual component operates, how the whole thing operates as one single thing, is just try to follow what each component is doing, and logically think about, okay, if this thing is doing this, and that thing is doing that, and that thing is doing that, how do they operate together? That is how I explain the processor from this point on. So are we good, okay? Are we okay with that concept? Okay, so there's some studying that is not based on written text, but I shouldn't say looking, but analyzing the design of the processor and understanding how it operates by observing, okay? All right, so what we'll do now is to focus on two of the composite items inside the processor. This is one, and this is the other one. This one over here is called a register bank, okay? A register bank is really just a bank of registers, and there's a purpose to a register bank. In the other class, I explained the register bank before I explained the ALU. In this class, I'll reverse it because it seems to make more sense to talk about the ALU first, and then we go back to the register bank. So this component over here is called the ALU. ALU stands for Arithmetic and Logic Unit. Okay, that's the full name of the ALU. And it is a component that is inside every processor. If you look into the Intel architecture, like the architecture, i3, i5, i7 architecture, each core has multiple ALUs. Okay, so if you have a quad-core processor, then you have 4 individual cores. But within each core, there are 3 or 4 integer ALUs. So that means at any particular time, your Intel processor can carry out multiple integer addition, subtraction, and comparison all at the same time, which is really amazing if you think about it, okay? So let's say each core has 3 ALUs, okay, integer ALUs, because they also have ALUs specifically for floating point calculations. So let's just count integer ALUs. If each core has 3 and you have a quad-core processor, which is not even that big of a deal these days, right? I mean, you buy most computers, especially desktop computers, they're all quad-core at least, okay? So you have 12 ALUs operating at exactly the same time all the time. And that's a lot of computation power, okay? So this is the inside of one single ALU. So we'll start with the heart of everything, okay? What is this? What does it look like? Is an adder. Okay, very good. It is an adder, and we spent quite a bit of time to talk about binary addition, and then we talked about carry ripple adder, which works. It's simplistic, but it doesn't work well because it takes too long for the carry to propagate all the way to the end. Do you guys still remember that discussion? So I want to kind of bring up these discussions, once in a while so that we can relate what we are seeing with something that we have already talked about, okay? So then we talk about carry look ahead, which is a faster, much faster mechanism when it comes to an adder that has a wider bit width. So this is just an adder, okay? We are not looking into the adder itself anymore. We just say that, okay, what are the ports, okay? What are the interfaces or parameters to an adder? There are 3 inputs. This is the first input. It's carry in, which we know as K0 in our terminology. And this one is kind of hooked up to a constant of 0 instead of another pin. But I'll explain why that is the case later on. We have this one as one of the numbers to add. And then this is the other one, which is the other number to add. So it kind of makes sense, right? One is X, one is Y, and the pin or the port at the top is K0. So we kind of know that part from what we have done with adders already. As far as the outputs are concerned, there are 2. This is the actual sum, okay, what we know as the S port when we talk about the adder. And this is the carry out, okay? With a 3x3 adder, this is our K3. This is an 8-bit adder, so this is technically this is K8, okay? So do we understand the ports or the interface to an adder at this point? No big surprises here, right? Okay, so the job of an adder is quite simple. Give me 2 numbers and potentially 1 carry input, and I'll just add everything, okay? Give you the output and also give you the carry flag as a part of the output as well. But now the question is, what are we adding? So this is something that I would do a lot from here on, is I'm going to look at the diagram and I'll start to track the wires backwards and sometimes forward. I'll start with the core operation that I want to explain, and then we'll track it backwards, like this wire here. This wire goes back to a multiplexer, a demultiplexer, excuse me. It goes back to a demultiplexer. What does a demultiplexer do? Since this is like only the 3rd time, third lesson that we have talked about the demultiplexer, so we'll kind of spend a little bit of time to kind of make sure that we understand what is a demultiplexer. What does it do? It's like a train track switch. It has 1 input and multiple outputs, okay? So in this case, the input is coming from the input pin called in0 in this case, and it has multiple outputs. The outputs are labeled from 0 all the way to 7. But only the 0 is labeled because everything is just kind of sequential after that. What is the switch mechanism? How do we know which way to switch? So So, okay, so there are 2 additional ports. Which one controls the way it switches? The one with a gray dot. Very good. So the one with a gray dot is what we call the selection, okay, or select. So that itself connects to OPSEL, or operation selection. Because there are potentially 8 outputs, it would take 3 bits to select one of the 8 outputs. Does that make sense? Because 0 is 0, 0, 0 as 3 bits, and 7, which is the last one, is 1, 1, 1 in bits, in binary. Is that okay? All right? So this one here, which is the green wire, goes to an enable, okay? In other words, I have a way to shut down the entire ALU so that I can minimize the consumption of electricity. Okay, so the green wire is here only because I want to be able to save power. Okay, otherwise it's not actually necessary. So are we doing okay so far? Okay, so we can kind of imagine the OP cell is 0, 0, 0 at this point. So whatever is presented to in1 is going through the demultiplexer and is going out of output 0 and is going into one of the numbers to add with the adder. So I'll be okay with that concept. Yes? Okay. What about the second number that we are adding? It's the same deal, except it doesn't go to the first or the top demultiplexer. It goes to the second demultiplexer. But in terms of how it is connected, it's almost exactly the same as the first one. It has its own input pin, which we call in2, but it connects to the same operation select bits. Are we getting this? Okay. So however I switch the first demultiplexer is exactly the same way that I switch the second demultiplexer. It's just that one is coming from one particular input train track, the other one is a separate input train track. But the way I control the switches is parallel. If one is connecting to output 0, so is the other one. So are we good so far? Yes? Okay. So what happens to the result of the calculation? So the result of the calculation is coming out of the output of the adder, and it goes into a multiplexer. A multiplexer is the reverse of a demultiplexer, as most of you probably know just because of the name. So with a multiplexer, we have multiple inputs, and by using the select pin, which is the one under the gray dot, we can say, okay, there are so many inputs, but which one should I connect to the output? That is controlled by, once again, operation select. Is that okay? So now we have 3 switches, and they're all parallel in the sense that the which input or output it is selecting to the other side, they are all the same. So this multiplexer will take input 0 and present whatever input 0 is to the output pin, which is the result of the ALU. Are we good so far with this? Okay. Okay, so that part doesn't seem too difficult. So we'll just take a quick look at the other operations that the ALU is also capable of doing. Okay, this is the first one. The adder is the first operation we can perform, which we know as operation 0, okay? Because OPSEL has to be 0, 0, 0 to make use of the adder. This is a subtractor, okay? Operation select has to be 0, 0, 1 to make use of the subtractor. This is right shift. So right shift is number 2, 0, 1, 0. And then we have bitwise NOT. So it looks like just like a NOT, but it's multi-bit, so it's a bitwise NOT. It will flip every single bit from the input to become the output. Is that okay? Yes? Sorry, what was the middle one again? The middle one, this one? Yeah. Is right shift. So this number coming in is right shifted by the position controlled by this wire. So you can right shift up to 7 times in this case, because the number of shifts you can specify is only specified by 3 bits. So with 3 bits, you can only specify up to 7. So you can right shift by up to 7 bits, depending on what the second input is specifying. Okay? This is bitwise NOT, this is bitwise AND, and this is bitwise OR. That's it. That's all we can do with this particular ALU. I have the room to add 2 more operations because you can see 2 outputs of the multiplexers and the demultiplexers are left unconnected. So that leaves me a little bit of room to specify further operations, but I do not have the need to do any of that yet. Are we doing okay so far? Okay. So we also see a bunch of wires and tunnels going someplace else. So now it's time to explain those, and that will bring back the topics of binary number comparison. Okay, if you guys remember, binary comparison, we have signed versus unsigned comparison. With unsigned comparison, we make use of the borrow flag. With signed comparison, it gets a little bit complicated and crazy because we have the sign flag, which by math should be able to tell the ordering of the x and the y, or the minuend versus the subtrahend. But because a number can be out of range or overflow, the sign flag may not give us the correct answer. So we have to look at both the sign flag and the overflow flag in order to decide is the minuend less than the subtrahend? Do you remember, vaguely remember that crazy talk about sign number comparison? Yes? Okay, very good. So what we'll do is we are going to take this whole thing apart and say, well, do we have any capability of using those flags or generating those flags in this design? So the first thing we might notice is all the way up here. This is a tunnel. It's called S1. But what is S1? S1 is going through a very deformed splitter to connect to the first input. So if you can read, well, some of you may be able to read, but it's a very small 7 right here. So we are taking bit 7 of in1 and turn and say that, okay, this now has a special name of S1 as a tunnel. Is that okay? We don't quite know how we're going to use S1 at this point because we will see it later. And then we see that S2 is also bit 7 of in2. Is that okay? We see that S out is bit 7 of whatever the output is, whatever is the output of the calculation. Are we good so far? And then we see this crazy thing down here, okay? This crazy thing down here is a 8-bit splitter. It splits all 8 bits into individual wires, and then it feeds all 8 bits into a bitwise OR that has 8 inputs. Whew, that's a mouthful. Okay, let me say that one more time then. It takes all these 8 bits, okay, as a single wire. It splits the 8 bits in a single wire into 8 individual wires. And then it takes each bit into one input of an 8 input but 1 bit OR. So what is that going to do? It's like bit 0 or bit 1 or bit 2 or bit 3 all the way up to bit 7. Yes?
Isn't that a NOR?
This is a, yep, you're right. This is a NOR because of the little bubble here. So thank you. Thank you for the correction. It is a NOR. It is indeed a NOR. Okay. So the question is, what is it going to do? Well, okay, let me ask you this question then. Okay, I'll flip the polarity of the question. Under what condition would Z out as a tunnel or this wire be a 1? Now this is a NOR, which means it is the negation of OR. The input is 0. Very good. Okay. If the input or if the output of this multiplexer is just 0, which is 8 zeros, okay, 8 binary zeros, only in that case will Z out be a 1. Okay. So if that is the case, can anyone guess why this is called Z out? What is the Z representing?
0 and 0.
Or zombie? It's 0. Okay? Sum starts with an S. So it's 0 out. So the 0 flag, which we never talked about before, is a binary thing or a Boolean thing. It is 1 if and only if the result of a calculation is 0. Okay? Anything other than 0, Z is going to be 1. Other than, okay, any result of non-zero will end up with the Z flag being a 0. Is that okay? So the Z flag is a 1 if and only if the result is, in fact, 0. Okay? So that will become useful later on, okay? But right now we want to know, okay, what are we doing with S1, S2, and S out? S1 turns out to be, if I specify a subtraction, S1 is the minuend, or the sign of the minuend. If I specify a subtraction, S2 is the sign of the subtrahend. And if I specify a subtraction, S out is the sign of the difference. Have we heard of those phrases before? The sign of the minuend, the sign of the subtrahend, and the sign of the difference. Used in what context? Overflow flag. Very good. So if you scroll down on this particular sub-circuit, you will see this little thing here, okay? So we'll focus on this part. Okay, let me just kind of select the part that we want to focus on, which is only this part here, okay? So if you only focus on that part, what does that look like to you? Okay?
Hard to see with all the little buttons.
Yeah, with all the selection thing, okay. Okay.
'Cause I think like there's a knot or two. But
Yeah, but it's hard to tell, right? So let me see if I can position it so that it is something that you can focus on, like that. Okay, would that help?
yeah.
Okay. So remember, S1 is the sign of the minuend, S2 is the sign of the subtrahend, S out is the sign of the difference. So what is this sub-circuit trying to calculate? The overflow. So the overflow flag can be implemented in hardware using logic gates like this. Okay? So not surprisingly, the output eventually becomes the O flag. Okay? So we'll follow that line. Okay? I'll stay zoomed in just so that we can kind of focus on one thing at a time. It goes through another multiplexer. So this is a strange little multiplexer because for everything else, it connects to O in, overflow in. But only for operation 0 and operation 1, it would actually do some calculation. So what this means is for anything other than addition and subtraction, it would just say, well, whatever I see as the input pin of overflow, I'll keep it as the current overflow. I'm not changing overflow. So there's no sense to talk about overflow when you are right shifting. There's no sense to talk about overflow when you're bitwise knotting, bitwise anding, or bitwise oring. It only makes sense when you're adding or subtracting. Are we good? Okay. But the way we compute overflow is different. When you're adding, it is different when you're subtracting. So that's why there are two sub-circuits to compute overflow, one for addition and one for subtraction. Do you see everything that relates to addition always hook up to pin either input or output pin 0? Yeah. Everything that has to do with subtraction is always 1. Okay? That is the overall architecture of the ALU. Is, there's a whole bunch of multiplexers and demultiplexers so that we can say, oh, this circuit is now doing an addition. This circuit is now doing a bitwise AND. This circuit is now doing a bitwise subtraction. And we focus only on one path, of all the possible paths inside the ALU. Is that okay? All right. So this multiplexer outputs to O out, which is overflow output, which goes into a pin, and we'll deal with that later. What about the other one? What about this multiplexer here? Okay, you may not remember, but that's okay. Where do you think the tunnel C comes from? Carry, okay, from the adder. What about B?
Borrow.
From the subtractor, okay? So with addition and subtraction, the carry and the borrow has meaning. And as a result, when they have meanings, they come from the adder or the subtractor through the multiplexer to become what we know as the carry bit as the output of something. Is that okay? So we cannot differentiate between a borrow flag and a carry flag after the operation because they merge basically into one single flag. It doesn't make sense to talk about either carry or borrow when you're talking about bit shift. Okay? Now there are some processors where the carry bit is whatever bit is shifted out of the shifter, but the shifter that we use does not have the capability of remembering which bit is shifted out, so it doesn't make sense. It doesn't make sense when you're bitwise knotting, bitwise anding, and bitwise oring, and that's why all of those just connect to the current state of the carry bit. Okay, we'll look at what C-in is connected to later on. So are we still doing okay in this design here? Yep.
So you mentioned that some ALUs, like this one, have, for example, the carry bit, and some don't.
Mm-hmm.
Is there a way to tell when we're using an ALU whether or not they have that feature, or do we just have to get?
Yes. So when you read a processor's data sheet, it will tell you what each instruction does, And in the documentation of the instruction, it will tell you, whether the carry bit has any special meaning, like which bit does it get, or does it not affect, the carry bit at all. So there are specifications like that. Okay, very good. So now we see a whole bunch of stuff coming in through a merger, and that becomes the output. So we have our carry flag, which is kind of like a merge between the carry from an adder or the borrow from a subtractor. We have the 0 out, okay? Now remember, the 0 flag is affected by every operation. It is not only affected by addition or subtraction, it is also affected by bitwise NOT, bit shift, bitwise AND, and bitwise OR. Okay? If the result of any operation is a 0, the Z flag is going to be a 1. That is universally affected. Okay? The sign flag is the same way. If bit 7 of the result of any operation is a 1, the sign flag is going to be a 1. But tech, we are doing an operation where the bits should be interpreted unsigned. It's okay. Then you just look at the sign flag as bit 7. Okay? Then you might say, but for unsigned numbers, bit 7 is for the most part useless. Then ignore it. Don't use it. Okay? But I want to emphasize that it does get affected by every operation. The overflow flag is only affected by addition and subtraction. Otherwise, it is preserved, okay, in quotes. Then you see something extra here. You say, well, what are we doing with this? This is exclusive OR, right? What are we exclusively ORing? We're ORing the overflow and the sign. So the output is what we call the L flag. Okay? It is just the L flag is only significant when you want to see in a subtraction whether the minuend is less than the subtrahend. That's its only purpose of life, which is actually quite important in many programs. Is that good so far? Okay? So all of these bits, 5 of those, would merge into one single output pin, which I call flags out. Okay? The output of the flags. Is that good? Okay? Okay, just one more little thing to the other side, and we are almost done with the ALU. So the other side of the ALU looks pretty simple. It looks just like that. All it does is to go through a weird splitter. This is a splitter that is 5 bits wide. Okay? But of the 5 bits, we only take 2 of them out. Bit 0 goes to C in, bit 3 goes to O in. What about the other flags? They're ignored, dropped. Okay? Because only these 2 may potentially is needed to be mirrored on the output. So if you're performing a bitwise NOT, for instance, whatever C in is seeing becomes C out. It is preserved. If you're doing a bitwise AND, for instance, whatever overflow flag is coming in is whatever you're mirroring out, so it is preserved. Are we good with that? Okay, because those operations really should not have any effect on overflow or carry, because it doesn't make sense. Is that okay? So this is the ALU. So if I zoom back out, the ALU looks a little bit complex because it does have quite a few components. But when you look at how the components work together, it is not too complex. I hope it's not too complex. Is that okay? So in the next exam, in exam 2, you probably want to bring a printout of the ALU, because you can bring whatever material that is either printed or handwritten prior to the test. So one of the things that you might want to bring would be the circuitries that we talk about in this class. Is that okay? Now on top of that, I'll give you another possible hint, okay? Some of you may want to know these, the locations of the flags and the location of the gates well enough. So if you just say that I cannot remember where overflow flag is computed, okay, on your piece of paper, draw a rectangle here and then point it out and say this is how we compute overflow. Because on the piece of paper or as a PDF, you can add your own annotation. Yes?
How would we print out diagram of the ALU.
Very good question. How do we print out a sub-circuitry? So you go to print, you go to file, and you can either print here, okay? So if you go to print, it will give you some, parameters. It will ask you, which circuit are we printing. So when in this case, even though we are looking at a sub-circuitry inside main, but right now we are printing main. So you have to double check and see which one you're printing. The header is what is displayed on the top of the piece of paper. And here you want to, if the circuitry is like this, then it makes sense to print it in portrait mode. If it is like the main processor, it makes more sense to print it in landscape mode. So this is really just asking, should I rotate to make it fit? Otherwise, it will use portrait mode by default. Okay. Since you're not turning in this printout for submission purposes, so you probably want to rotate to fit just to make the most use out of your piece of paper. Okay. The last one is printer view, and I'm not quite remembering what printer view does. I know that, well, let's give it a try, right? I mean, that's easy. So we'll print it with printer view. Click OK. And unfortunately, it's being printed to a printer that does not exist because I'm not at home. So the default printer does not work. So let me change my default printer first so I can capture it as a PDF. Then we can look at the PDF. Then we can see what it would look like. It would have looked like if I did print it on a piece of paper. Okay, so I go to print settings and change these. It doesn't have a PDF printer on the list. Okay.
Is there no way to export?
Not directly from inside Logisim. So I'm going to add a new printer. And we want it to be a PDF printer. Can we specify PDF?
Yes.
There we go. Okay. But where is it going? Where's the output? I don't know whether it's sent to a file or not. Okay, device URL. How do I specify a file?
Location.
Not the location. This is just text. I can
Look at your
cheat.
recent.
Hmm?
You can look at your recent files and see if that shows up.
Okay, I'm just cheating here. Looking up. There's no easy way to do it. Okay. Okay, let me show you the other way then, since I cannot get this to work. Okay, so the other way is to export it. So you can export the circuit into one of these three formats. My recommendation is PNG, because if you export it as JPEG or GIF or GIF, it's going to be lossy. So some of the pins would look not so sharp anymore. So my recommendation is to export as PNF. The scaling factor allows you to scale up and scale down, obviously. And okay, now I remember what is printer view. In printer view, it would not have the green wires and whatnot. It would actually it would assume nothing is active. So it's not going to use color coding. And instead, it will give you a much more generic type of output, which I think is the better option. So if I click OK, it should ask me where that thing is going. Nope, it did not. Export image. It doesn't ask me where, or maybe it's in a different window. Nope.
Where would it go by default?
That's a good question. Let's close this. Okay, let me go back to main and do it one more time. Okay. Okay, so you can only do it when you're in the circuit that it has named. Okay, there we go. So now we can name the file as tmp ttp.png. .png is going to be automatically appended, so just export here. And now we can open that file. So we go to the temp folder and look up ttp.png, and this is the actual bitmap. Now, since this is, can you guys see it?
It's very cropped.
Huh?
It's very cropped.
Yeah, well, that's okay because, I just wanted to show you what it looks like. Yeah, so this is the printer view, and you don't see the green wires or the red wires and stuff like that because it is inactive. The whole thing is just inactive, and it will only use black and white and grayscale to print this out. But this is just a bitmap, which means now you can import that into another program like Microsoft Word or Google Documents or whatever. Then you can start to annotate it. Okay, you can add your own annotation. You can use your own color coding. You can use your own whatever to kind of make it more readable from your perspective. Okay, so that's something that you can consider doing even now, is to start to annotate the processor design with your own words and your own understanding, so that way it is a way for you to study as well as to prepare for the next exam. Is that okay? All right. So because this is just a PNG, I mean, you can do whatever you want as a bitmap. Okay, very cool. All right, so we are now done with the ALU, or the explanation of the ALU. So one thing we notice about the ALU, which looks deceptively small, in the overall circuit, is it takes two things most of the time, and it comes up with one new thing. Does that make sense? Give me two numbers to add, I'll give you the sum. Give me two numbers to subtract, I'll give you the difference, and so on. So now the question is, where are we getting those numbers for the ALU to process? It's the register bank. Okay? So for the most part, we want to use the register bank to supply what we need in order to perform the calculations. Addition, subtraction, bitwise NOT, right shift, and so on. We want those things to come from the registers. Where are the registers? The registers are located in the register bank. And the register bank is a much simpler circuit compared to the ALU, because all it does is to house 4 different registers. So there's register A, B, C, and D inside the register bank. So there's one immediate question is, well, then what is the difference between these 4 registers compared to the other registers that are also in the main processor design? Okay, I'm just switching out a little bit so I can show you what the other, quote-unquote, other registers we are talking about. We have the flags register here, okay, which is what we use to remember the flags, okay, the Z flag, the S flag, the O flag, the L flag, and so on. We have a register here that has a name of program counter, okay, we call it PC just for abbreviation. We have another register called the instruction register. We have another register here called the microcode pointer. So what makes the registers inside the register bank different from the rest of the registers? One key difference. These are software accessible. The other registers are not software accessible. In other words, excuse me, when we get to actual programming this particular processor, in the instructions that you choose to use, you can say, oh, I want to pick register B to become the first input of the ALU, and I want to choose register D as the second input to the ALU. You can do that, okay? You, as a programmer, as a software developer, has that choice. The other registers that we saw, the program counter, the flags register, and so on, you don't get to choose which one to use or how to use them. These you do. Is that okay? So these are special because you can specify which one you want to use in software. The rest, you don't have a control. You don't have any control over those. Is that okay so far? Okay. All right. So we got 4 registers, and then so one thing you can also one way you can look at the circuitry is look at the circuitry from this perspective of the pins. Because the pins are the interface into the circuitry, so each pin should have a meaning of some sort, okay? So we can start with this input pin here and go like, okay, it's called register in, R-E-G-I-N. Where does it go, okay? Now you can select the poking tool, which helps you identify the entire net that that port is connecting to. So you can see that it connects to all the D ports of all 4 registers. Okay, that sounds kind of suspicious, okay? Then you try to look at the clock, okay? The clock is down here, and you say, how is it connected? It's also connected to the clock port of every single register. You look at the reset, same way, it connects to every single register. So all the pins that we have clicked on so far are multi-dropped, which means they come from the input pin and they are connected to every single register in the register bank. Then it goes like, it doesn't make sense, because why would I want to update all 4 registers at the same time to the same content? It just doesn't make sense. So now you have to look into the enable pin, okay? So the enable pin is right here. Oh, so the enable of the first register or register A goes to output 0 of this decoder. The enable of register B, register C, and register D. Okay, so we have a decoder to connect differently to the enable of the 4 registers. What is a decoder? You can look at a decoder as a demultiplexer, where the input is a constant of 1. Okay? So you just kind of imagine that there's another pin coming out of here, and it connects to a constant 1. That's basically what a decoder is. Other than that, a decoder, just like a demultiplexer, has a select pin. And in this case, the select pin has 2 bits, because we have to select one of the 4. Is that okay? So that means in order to update a register, you need to do 3 things. 1, tell me the content, the new content to overwrite the register. 2, tell me which register you want me to overwrite using register input select. 3, enable the decoder. Okay? Okay, I lied. There are 4 things. Rising edge at the clock. That would actually trigger the update of the register. Is that okay? Yes? Okay. Okay, so that kind of explains the west side of the design. So now we look at the east side of the design. So we start with the register output 0 as an output pin and register output 1 as an output pin. They are pretty much the same thing, okay? So you look at this one and go like, okay, we see the output of the multiplexer is going to the output pin, but where are the inputs coming from with this multiplexer? Okay, input 0 comes from register A, input 1 comes from register B, input 2 comes from register C, and input 3 comes from register D. Okay, but this is a demultiplexer. So which input do I actually use to come up as the output? It is selected by register output 0 select. Whoops. Is that okay? And register output 1 is kind of the same deal, except the select is a different pin called register output 1 select. Yep.
What was that message that just showed up about super state?
I do not remember. I think I made that happen by double clicking. This pin is tied to the super circuit's state create a new circuit state, and the answer is
Good.
no.
Okay.
Because this is a subcircuit of the main processor, so what you're seeing right now are the states from the main processor. This is not independent by itself. So the question is, do I want to make a new instance of the register bank so that it has its own state that is separated from the main processor? That's what it was asking me. Okay, so what is this used for? In the case of the ALU, what do you think this stuff is going to be useful for? Okay, what does the ALU need for most operations? Most operations means all operations besides bitwise not. It needs 2 inputs, right? Okay. So now I can say, I can connect register output 1 to the first input. I can connect register output 1 to the second input. But not only that, I can say, oh, I want register A to be responsible for register output 0, and I want, let's say, register D to be responsible for register output 1. Do you see what this is doing? I can select any one of the 4 registers to become output 0 from the register bank, which connects to in 1 of the ALU. Likewise, I can select any one of the 4 registers to become output 1 of the register bank, which becomes in 2 of the ALU. So now I have 16 possibilities. Okay? If I'm just talking about addition, I have 16 possibilities because I can add register A to register A. I can add register A to register B. I can add register B to register C, and so on. Now, addition is not really too good of an example because adding register A and register C and adding register C and register A are the same thing because addition is commutative. But when it comes to subtraction, it is not commutative. Okay? Then we have uniquely 16 different ways of subtracting using the registers. Is that making any sense? So this gives us the flexibility of saying, which 2 are we adding? Okay? Or are we subtracting? Which one specifies the bit pattern and which one specifies how many bits to right shift? Okay? What about the input? Well, the question is, once your ALU is done adding, subtracting, bitwise ANDing, ORing, bit shifting, or bitwise NOTing, okay? What are you going to do with the result? You might want to store it back, okay? Most of the time you might want to store. So this side allows you to specify where am I going to store the result back into. Is that okay? So the register bank is really an abstraction, so that the circuit looks a little bit easier to understand, so that we can specify which numbers are we operating on and where are we storing the result of the operation. Is that okay so far? All right. So this is a good time to kind of segue a little bit into some material that you need to look up and understand in order to do the lab. So I'm going to go into that a little bit. So this class is now slightly behind the other class, about synchronized at this point. So right now you are benefiting from what I learned from the other class for the first time. We caught up. The other class caught up, actually. They were behind. Okay, so when you go to processor, there are 2 documents that are particularly useful for this homework assignment or lab. One is a spreadsheet called opcode table, which is this one. And we'll open it on the side. And another one is called the assembler manual. Okay, so these 2 documents are particularly useful. Most of the information you can find it here in opcode table. Okay, so the other one, you can kind of read it because it has general information that you might find useful, but this is the one that is particularly useful, so you might want to focus on this one. And one of the questions asked about subtraction, so I will leave that up to you. So instead of talking about subtraction, I'll talk about addition. All right.
What was the name of the other file?
It's called assembler manual. which talks about how to use the assembler, how it works in general, blah, blah, blah. This one talks about instructions, okay? So inside the processor, each opcode, which is represented by column A, specifies a particular operation, okay? So column A is what the computer or what the processor understands, and then column C and column D are intended for you, so that I can explain what it is doing. Is that okay? So when you look at row 26, it talks about the opcode of 1000. These are binary numbers, by the way, XXYY. So what is XXYY? Well, you got to read the rest. The mnemonic, which is column B, mnemonic, by the way, is a slightly more user-friendly way to refer to an opcode. So unless you guys want to remember opcodes by zeros and ones, okay, you might want to start to use mnemonics, because mnemonic is a little bit easier to understand, even though it can still be cryptic in certain cases, but it's still better. So it says add XY. This is what the assembler actually recognizes, okay? So when the assembler sees add some register X and some register Y, the assembler will convert it into a byte that has the bit pattern of 1000, and then XX would be the bits to specify register X, and then YY would be the bits to specify register Y. Is that okay? And this is the C representation of what the opcode actually does. Register X gets register X plus register Y. That's what the opcode is going to do. It will take two registers, add the two registers, and then store the result, which is the sum, back into the first of the two registers. Is that okay? And the English explanation here is just add. That's not much to say. Yep.
For those opcodes which only have two registers, is the other register just not touched, not used?
It is only read but not overwritten. So YY in this case, or register Y, is read, but it is not changed.
What about for row 24?
For row 24, we'll deal with those later. Those are more difficult ones to explain.
But so is YY touched in those though?
In which one?
Row 24, for example.
So row 24 does not refer to Y at all. So that means there's no register Y to consider. Yep. Okay, so now the question is, what do you mean by register X and register Y and register XX and YY? Okay, the first one single row, two rows of the entire spreadsheet explains that, okay? So when you read the documentation, make sure you read it from top, and kind of scan around. XX specifies one of the four registers. For register A, XX is 00. For register D, for instance, XX would be 11. Is that okay? Are we understanding what is XY and what is XX and what is YY? This is not a genetic class, but in which case XX and XY would, then it says XY, but we don't have XY here. We just have XX and YY. Are we good so far? Yes? Okay. So this table is important because one of the questions would ask you something about what is the bit pattern of a particular subtraction in the lab. Okay, so you have to look up this table, understand what is register X. Register X is one of the four registers, A, B, C, or D. What is XX then? It will be the bit pattern to specify register A, B, C, or D. Is that okay? So if X is A, then XX is 00. Are we good? Okay. This is the entire instruction set of the processor. And you can see it's not a very long list. And this processor is also known as a RISC processor, RISC, which stands for Reduced Instruction Set Computer. Okay? Which is opposite to the Intel or AMD processors inside your laptop or notebook computer, because that one is called a CISC, which stands for Complex Instruction Set Computer. One uses the philosophy of we'll use the least number of instructions possible. so that we can make the die size, the actual silicon of your processor, as small and simplistic as possible. But then what about all of those complex operations that we want to perform? Well, we will just need to use more instructions. Okay? We can still do it. We just need more instructions to do it. Okay? As opposed to the complex instruction set computer, or CISC, which uses the philosophy of, I'll give you a bazillion instructions. Okay? So we can do a lot of things per instruction. But as a result of doing that, the processor die is now bigger. It consumes more power. It's a bigger processor die, and it has advantages and also disadvantages. So those are the two main philosophies when it comes to the design of a processor. The TTP is not a purist RISC processor. Okay? Okay, do you guys know what I mean by purist? Okay? It's not purist from many perspectives. Just looking at the ALU, okay, let me switch back to the ALU, will tell you why it is not minimalist. If I just go into the ALU and you look at this design here, why do you think this is not minimalist? I'll point to one thing. Well, okay, I lied. I point to three things, but it is referring to exactly the same thing. 1, 2, 3. Okay. Do you guys remember how I said, NAND can do everything? Yes? So instead of having bitwise NOT, bitwise AND, and bitwise OR, I could have gotten away with just a bitwise NAND. Okay? Now, yes, just because I can do that doesn't mean it's a good idea, because if I did that, then the operations I need to perform here if I want to do an actual bitwise AND, bitwise OR, or bitwise NOT, it gets a lot more complicated, and it's not worth that. It's not worth to save this much silicon to make the program this much more complex. So there's a trade-off between, well, are we spending silicon to make the software easier to write or more efficient to write? So there's a trade-off between those two. Okay? The other one has to do with the adder and the subtractor. Remember, we could unify adder and subtractor just by an exclusive OR, by negating or not negating x before we compute the p and the g terms. We can turn an adder into a subtractor and back the other way. So we could have done that. Okay? We could have done that and use a single circuitry to perform both addition and subtraction. But I did not do that, because that would not be a good use of silicon when these are the blocks that I can work with. Okay, yep, question?
You could combine the two overflow addition and subtraction into one.
I don't even need the L flag. Remember, if I can compute the L flag in hardware using an exclusive OR gate here, I could have done that in software too. But an exclusive OR gate is dirt cheap to include in a processor. But what it gives us is the simplification of the software by a large degree. So the sacrifice in terms of, we need to use, let's just say, 7 more transistors. But the amount of instructions it can save me down the line is a lot. Okay, so it's worth the trade-off. We are closing the end of the class. Let me just look at the time right now.
So
3 minutes. Yep.
you discussed that there's like simpler and more complex. The complex and the simple, and I don't remember their name acronyms right now.
CISC versus RISC. Mm-hmm.
So for those, would they, for the CISC, would it try to use a bunch of NAND gates, or is that not like CISC philosophy?
Ask that one more time.
Is it trying to make the commands themselves simple, or the processing simple?
You mean CISC or RISC? In
RISC.
In RISC. So in RISC, what we're doing is we are simplifying the instruction set. So the hardware can only do a few things. instead of a lot of different things. But the few things that we do implement in hardware, by combining those simple things that we can do in hardware, we can do everything that we need. In a CISC architecture, it is a different philosophy where each instruction can do more, and there are more instructions to choose from, so that you can say, oh, I want to do blah, 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 blah. Oh, guess what? We got one instruction just to do that. Oh, but I now want to do blah, 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 blah. Okay, we got another instruction, one single instruction that can do that. So you have a richer instruction set to begin with to choose from, but each instruction is also capable of doing more. But the sacrifice of a CISC architecture is you're using more silicon. So at the end of this class, I just want to point out one more thing, because we are already on the discussion of CISC versus RISC. Why? Right? Why your cell phone is always using a RISC type processor, but your desktop computer is almost always using a CISC type processor. So that's the question. What is the number one concern of a Fitbit? Battery life? Battery life. Very good. So a CISC processor turns out to have a much better power consumption, or power efficiency, I should say, compared to a CISC processor, because it has fewer transistors on it to begin with. So that means, how fast can your heart beat? Okay, I'm not an athlete, so mine can only get up to 160 or 170 beats per minute, which is translating to less than 3 beats per second, right? So some of you may say, but I'm much younger than you are, and mine can go 220 beats per minute. Fine. That is still less than 4 beats per second. Okay? Your Fitbit probably has a processor that is capable of running at, let's say, 20 megahertz. I know 20 megahertz is not a whole lot compared to 4 gigahertz of your desktop processor. But how many clocks are we talking about per heartbeat? A whole lot. Okay, we'll just say a whole lot. Okay, so do you think your Fitbit processor needs to be on the whole time and paying attention to the pulse sensor and whatnot? No. As far as your Fitbit processor is concerned, it wakes up. Okay, it take a look at a few things, jot down a few notes, increment a few point counters, store a few numbers, and it goes back to sleep. The sleep versus awake ratio of your Fitbit is probably at least 50 to 1 in terms of ratio. Okay? So for every 50 milliseconds that it is sleeping, it wakes up for 1 millisecond, do a few things, and then goes back to sleep again. I wish I could be like that. So now, what does this have anything to do with CISC versus RISC architecture? The fewer transistors you have on the processor die, okay, the less power it's going to consume during the sleep side of things. The more transistors you have, in order to keep those transistors in the state that they're currently in, it will draw more current. We call that a quiescent current, but it will draw more current just to maintain the state of the processor. So that is why your Fitbit wants to use a RISC processor as much as possible, because you want to extend your recharge time between 5 days, 6 days, 7 days. You don't want to have to charge your Fitbit every hour. That doesn't make sense. Now on your desktop, why are we using a CISC processor?
You have a constant power supply.
No, well, that affords it. Okay, that makes it quote unquote affordable. But the main reason is Microsoft. You go like, what does Microsoft have anything to do with this? Why do you drag Microsoft into this whole discussion? Well, that's because Microsoft is the center of the whole discussion. Okay? Every single processor on the desktop computer, all the AMD and all the Intel processor, they are backward compatible all the way to the original PC in the 80s. And you ask, why? Because the backward compatibility causes a lot of silicon in hardware. Okay? And that's because Microsoft operating systems is only supported on certain architectures. And Microsoft is the one who insists to have backward compatibility all the way back. Intel can protest and go like, but that is not good use of silicon. We want to make the processor as fast as possible while consuming power. Intel can complain, and Intel can say, I'm going to make a new processor that is not backward compatible all the way. Microsoft would then say, well, good luck, because now I will only certify AMD processors that are backward compatible all the way to be Microsoft certified. And guess who's going to buy non-Microsoft certified laptop computers? No one. So Microsoft actually can strong-arm, hardware manufacturers into continuing backward compatibility. And that is the main reason why we use CISC processors on desktop computers. Because guess what? This is left for the next discussion. Data centers, okay? When you look at Google, when you look at Facebook and all the data centers, they do not use CISC processors. They only use RISC type processors. So we'll continue that topic next time, and I'll explain why that is the case.
Just a spike.